Welcome to the deep dive. We're taking a plunge today into perhaps the most fundamental process in the universe.
Yeah, how stars actually build the stuff that makes up, well, everything.
Everything, including you listening right now. We're talking stellar nucleosynthesis. It's this incredible cosmic alchemy happening inside stars.
And our guide for this deep dive is, well, it's a really unique piece of writing. It's called Nucleo Extension Go Do. Nucleosynthesis extension to the standard model of particle physics for those who just have to have a laugh, by Edwin Campbell.
Right. And it tackles the super complex physics with a tone that is, frankly, hilariously bizarre.
The author calls it celestial cuisine meets thermonuclear vaudeville.
In an absolutely irredeemably absurd, but somehow still scientifically accurate fever dream.
Exactly. So our mission today is to kind of unpack this amazing text, try to understand this absurd but true process inside stars.
And figure out the really profound personal connection it has to you, the listener.
Let's dive in. So how do stars even, start cooking?
Right. Forget gentle simmering, apparently.
Oh, yeah. Stars, as described here, they're like cosmic ovens, definitely. But ovens run by someone with maybe some serious anger management issues.
Okay.
Take our own sun's core, for example. It's described as a 13 billion trillion ton cosmic cauldron.
Wow.
And inside, hydrogen is boiling at 15 million degrees Kelvin. Just immense.
The source really leans into it, calling it a place run by a deranged intergalactic soup chef with absolutely no chill.
Yeah, no chill whatsoever.
And it's not peaceful, right? It's framed as atomic pro wrestling.
That's the one. Protons bludgeoning each other into friendship.
That phrase, bludgeoning each other into friendship, it just perfectly captures the violent chaos needed, doesn't it?
It really does. And that gets us to the very first step, the real, main event. Getting those initial hydrogen atoms, which are just protons, to actually fuse.
Okay.
And they're just zipping around at these incredible speeds. The source says it's like Manhattan during rush hour, except every single particle is going 1,000 kilometers per second.
1,000 kilometers a second?
Per second. And they're all trying to fuse.
But wait, isn't there a huge problem? Protons are positive. They should push each other away, right?
Exactly.
Yeah.
That's the fundamental challenge. Positive charges repel. The source puts it very directly. Protons hate each other.
Like two grumpy old men yelling at each other. They just don't want to get close.
Right. So how do they possibly get past that repulsion, that electrical barrier, to actually touch and stick?
Yeah.
This is where physics gets really weird and kind of wonderful. The source says they basically cheat the laws of physics through something called quantum tunneling.
Quantum tunneling, okay.
Yeah, instead of needing enough energy to blast over the barrier, they can just sort of quantum sneak through it like cat burglars made of fire.
Quantum cat burglars made of fire.
Okay.
That's definitely fitting the scientifically accurate fever dream description.
They just pop up on the other side close enough to start snuggling up, as the source puts it.
Wow. Okay, so they tunnel through, they get close. Then what happens?
Then the strong nuclear force, which only works at really short distances, takes over and glues them together. But that's not quite enough.
No.
For the fusion to stick, one of those protons has to actually change into a neutron.
How does it do that?
That's the job of the weak nuclear force. And in the process, it spits out two tiny particles. One is a positron,
which the source calls
the electron's positively charged evil twin.
Right. And the other?
A neutrino. Described as a particle so socially awkward it immediately leaves the party and never talks to anyone again. Just zips right out of the star.
Okay, so a proton turns into a neutron, spits out an evil twin electron and an awkward neutrino. Leaving you with what?
Leaving you with deuterium, which is basically hydrogen with a buddy. A proton and a neutron stuck together. The source calls it hydrogen with a stylish new neutron hat.
I like that, a stylish neutron hat.
Yeah.
So that's the result of the first proton smackdown.
That's step one. Now, this deuterium, or hydrogen in its new hat, it doesn't hang around long. It pretty quickly bumps into another lone proton zooming around.
Then they fuse.
They do, yeah. They fuse to form helium-3.
Helium-3, so almost helium.
Almost. The source is clear here. It's not full helium yet. It compares it to a croissant that's only 75% baked. It's got two protons, but only one neutron.
Okay, so not quite the standard helium-4 we usually think of.
Exactly. So now you've got these partially baked helium-3 croissants floating around in the core.
What happens to them? Do they bake fully?
Well, eventually, two of these helium-3s find each other and collide.
And they fuse, too.
They do. And that's when you get your standard, stable helium-4. 2 protons, 2 neutrons.
Yeah.
Baked to perfection.
Ah, okay. So 2 helium-3s make 1 helium-4. Does anything else happen?
Yep. In that final fusion, 2 protons get kicked out. The source calls them the unwanted wedding guests. They just go back into the mix.
Unwanted wedding guests. Love it. So this whole sequence, proton plus proton makes deuterium, deuterium plus proton makes helium-3, and then 2 helium-3s make helium-4 plus 2 protons. That's the main process in the sun.
That's it. It's called the proton chain reaction.
Or, as the source prefers,
A subatomic conga line of creation.
perfect, because it just keeps going, right?
Yeah.
Generating energy.
Exactly. That's the fundamental energy source
Yeah.
for stars like our sun. And the main byproduct of all this fusing energy, pure energy,
Lots of it.
loads, mostly in the form of gamma rays, super high energy photons. The source calls them photons on an espresso bender, just vibrating like crazy.
Right. Now, you'd think these super energetic photons would just like zoom straight out of the star, wouldn't you?
You would think, but nope, not even close. The journey that energy takes from the core, where it's born, to the surface where it escapes is light.
Mm.
It's incredibly long and tortuous.
How so?
Well, a photon born in the core doesn't just travel in a straight line. It immediately bumps into an electron or proton or something. It gets absorbed, then re-emitted, maybe in a slightly different direction, maybe with slightly less energy. Then it travels a tiny distance, and bam, hits something else.
So it's like cosmic pinball.
Total cosmic pinball. The source says it's like trying to navigate a mosh pit full of rugby players in a fog machine. Just constant collisions.
Every time it tries to go straight, boom, another collision, just bouncing around randomly.
Random walk, yeah.
Yeah.
And because the sun is so dense, those steps are tiny.
Yeah.
So the total time it takes for the energy created in the core to finally reach the surface,
How long?
it's staggering. The source states it takes, on average, approximately 100,000 years.
100,000 years. Just to get from the center of the sun to the outside?
Yep. Give or take quite a bit, but that's the ballpark. It's an incredibly slow diffusion outwards.
Wow. So the sunlight that, warmed my face this morning, that energy was actually created.
Around 100,000 years ago, deep inside the sun,
Hmm.
back when humans were still figuring out tools and maybe hadn't even left Africa yet.
That's incredible.
It connects you directly to the sun's deep past. The source calls it prehistoric photon drama.
Prehistoric photon drama. I am definitely stealing that. Okay, so that's our sun. Hydrogen to helium via the subatomic conga line, and a very long wait for the light to get out.
Right. But that's kind of the basic model. What about the really big stars, the massive ones?
Yeah, they don't stop at helium, do they?
Not at all. Our sun is described by the source as hydrogen fusion light, big stars. They are the elemental Michelin star chefs of the cosmos.
Elemental Michelin star chefs. Okay, what are they cooking?
Once they burn through most of the hydrogen in their core, it contracts and heats up even more, enough to start fusing helium.
Helium into what?
Helium fuses into carbon.
Yeah.
Usually 3 helium nuclei combined in what's called the triple alpha process.
Okay, so hydrogen, helium, helium, carbon. Does it stop there?
Not in the big ones. If the star is massive enough, once the helium runs low, the core contracts again, gets even hotter, and starts fusing carbon. Carbon fuses into oxygen. Oxygen can fuse into neon. Neon into magnesium. Magnesium into silicon. It keeps going, like layers of an onion.
Each stage needing more heat and more pressure than the last.
Exactly. It's this constant battle against gravity. Fusion pushes outwards, gravity pulls inwards. To keep fighting gravity as the fuel runs out, the star needs to get hotter and denser to start fusing the next heavier element.
The source describes it as a
desperate high-stakes juggling act, with the star essentially screaming, more heat, more pressure, I need to fuse harder.
Wow, so it just keeps building heavier and heavier elements.
Yeah.
Until when? Is there an end?
There is. This continues layer by layer until the star's core starts fusing silicon.
And what does silicon fuse into?
Silicon fuses into iron. And iron is different. This, the source dramatically declares, is the wall.
The wall. Why? What's the big deal about iron?
Up until iron, every fusion step released energy. That energy is what held the star up against gravity.
Right.
But fusing iron, or anything heavier than iron, doesn't release energy. It actually consumes energy. It costs energy to make elements heavier than iron through fusion.
Oh, so the furnace just goes out.
Pretty much. Iron is the most stable nucleus. You can't get energy by fusing it or by breaking it apart easily, so the iron just builds up in the core. The source says it sits there like a judgmental X.
A judgmental X ending the party.
Exactly. It ends the energy production in the core. silently.
And without that energy pushing outwards,
Yeah.
what happens to the core?
Gravity wins. Instantly and catastrophically. The core, which is now just this growing ball of inert iron, collapses under its own tremendous weight in less than a second. And that collapse triggers the grand finale, the most spectacular death imaginable for a massive star, the supernova.
Boom.
Boom is right. A supernova. And this isn't just some pop. The source calls it a thermonuclear detonation so intense it briefly outshines entire galaxies.
Outshines galaxies.
For a short time, yeah. It's the universe's way of, well, the source says rage quitting.
Huh. A cosmic rage quit. But this unbelievable violence, it's not just destruction, is it? This is actually where the really heavy elements get made.
Precisely. All the elements heavier than iron in the periodic table, they aren't made during the star's normal life. They're forged in the hellish conditions during the supernova explosion itself.
How does that work?
The collapsing core rebounds, sending a shock wave outwards through the star's outer layers. You have this incredibly dense flood of neutrons, insane temperatures, unbelievable pressures. Atoms are just smashed together with tremendous violence.
So things like gold, platinum, uranium.
All of that stuff. All the really heavy hitters, basically all the fancy stuff humans use, as the source puts it. They're created in those fleeting violent moments of the supernova.
Wow. So the star lives its life making elements up to iron, and then in its death throes, it creates everything else.
Pretty much. And then it blasts all those elements, the ones made during its life and the ones made in its death, out into space.
Dispersing them.
Dispersing them. Hurled across the cosmos like glitter from a vengeful drag queen with godlike powers.
That is quite an image.
The source loves it. It concludes that section saying, "Stars die fabulously," which honestly feels about right after hearing all that.
Yeah, fabulously and incredibly productively, it seems. Okay, so we've followed the journey. Simple hydrogen fusing, quantum cheating, building up helium.
Then the bigger stars doing the heavy lifting, carbon, oxygen, all the way to iron.
Hitting the iron wall, collapsing, exploding in a supernova.
Creating gold, uranium, all the rest, and scattering it all.
So what's the punchline? Why does this cosmic drama matter to, well, to me listening right now?
This is the absolute core takeaway. The reason this whole, frankly, absurd process matters, you, the listener, are made of this stuff.
Literally.
Literally. You are made of the ashes of exploded stars. The common phrase is stardust, right? But this source really nails it down.
How so?
Think about it. The calcium in your bones and teeth, that was fused inside a star. The iron atoms in your blood carrying oxygen right now, those were forged layer by layer in the heart of a massive star just before it died.
Wow.
Even the lighter elements, the carbon, the nitrogen, the oxygen that make up most of your body, they were cooked up through these fusion processes we've been talking about. And maybe even some atoms in your brain, the ones letting you think about this.
They could have been made in a supernova.
They could have been part of that atomic pro wrestling match or forged in the final explosion. You are not just like stardust. You are stardust. Animated stardust.
So I'm basically a walking, talking collection of atoms that were inside stars billions of years ago.
You got it. The source puts it brilliantly. You are a living monument to a star that exploded billions of years ago.
That's humbling.
And it gets better. The source says the universe essentially looked at your carbon-based form.
Which it called a call.
A meat popsicle.
Right, the meat popsicle.
Looked at the meat popsicle and said, yes, this meat popsicle shall ponder its own atomic ancestry.
Pondering my meat popsicle ancestry. Okay, that's a perspective.
The source had a TLDR, right? A summary.
It did, yeah. It basically boils down to stars are fusion machines. They use physics and quantum cheating. They make new atoms. Big stars die spectacularly, flamboyantly.
Right.
That stardust gets spread everywhere. And eventually, that stardust becomes us. You.
And the universe itself is
a chaotic, flaming nonsense fireball. And we are within it. Confused, sentient sparkles.
Confused, sentient sparkles made from a chaotic, flaming nonsense fireball. It sounds completely bonkers.
It does. But scientifically, it's pretty much spot on. That's the amazing thing.
It really is. So there you have it, this unbelievable cosmic journey from, hydrogen atoms smashing together inside a star.
Through quantum weirdness, stellar cooking, hitting that iron wall.
To the mind-blowing violence of a supernova creating heavy elements.
All leading, billions of years later, to the very atoms that make up your body right now. The sheer scale of time, the energy involved, the just sheer improbability of it all is kind of staggering when you think about it.
Absolutely. And it leaves you with a really fascinating thought, doesn't it? This whole picture knowing we're literally built from the remnants of ancient, violent, stellar events happening light years away.
Yeah.
It makes you wonder, what other deep connections, maybe ones we haven't even dreamed of yet, exist between our everyday lives or mundane existence and the vast, truly strange things happening out there in the cosmos?
That is definitely something to ponder. Maybe next time you look up at the night sky. Or maybe just next time you look in the mirror.